Hello and welcome back to BME 2315. In today's lecture, we'll be talking about nonlinear regression. So far, we've been studying linear regression, which meant when we were feeding in various different data sets, and if we found that they were linear with respect to the parameters, we can cast this in a matrix form and get a unique solution that is a best fit solution to that data. Today, we're going to be looking at a more advanced techniques in nonlinear regression that can help you solve to nonlinear models when there are no good linear models available. So some of the, because this builds on the past lecture, it's important to review some of the key points from that past lecture. The first is that what do we mean by regression? What we mean by regression is that we're fitting models to data, usually by minimizing the sum of squared error. The sum of squared errors. And linear algebra, and one of the nice things about linear regression, as we found so far, is that it has unique solutions. That means that there's only one solution that fits what we're looking for, and that allows us to find and calculate the coefficients algebraically, which is very convenient. And we also talked about ways in which we can quantify the regression error. One of those is called the sum of squared errors, which is what we are minimizing, and the other is the coefficient of determination. And that's nice because coefficient of determination tells us what percent of the data can be captured by that regression model. And so using these forms, we found that we could use linear regression to fit lines through data, but we could use general linear least squares, a broader matrix-based version of that, to fit surfaces to points in three-dimensional space, or even fit polynomials that are nonlinear with respect to x, but linear with respect to the parameters. And we'll kind of delve into what we mean by that in just a minute. But basically, what we found here is that this general linear least squares is a very powerful technique that allows us to do many different types of fitting problems by a few algebraic matrix calculations. So some of the other sort of key points from that is that we were able to formulate our problems as matrices. And these linear least squares models could be extended by general linear least squares to equations with multiple independent variables. That's like the surfaces or nonlinearities in the equations, as long as the equations are linear with respect to the parameters. And that's a very important property, being linear with respect to those parameters. Okay, so because that's such an important property, let's dive in and kind of take a closer look at what we mean by that. So how do you tell if a function is linear with respect to parameters? Well, if you take the partial derivative with respect to that parameter, there should be no parameter terms left. And so let's take a look at a few examples of this. So in these two examples, we had this like a line or lines with multiple independent variables. These are linear with respect to both parameters and variables. Right? You don't see any parameters multiplied by parameters and such like that. So if you took a partial derivative with respect to b0, and b0 will drop out of the equation. You take the partial derivative with respect to x1 will drop out of the equation. Okay. There's another set of equations that we can also use in general linear least squares, cases where things are linear with respect to parameters, but not variables. So you see you got x1 times x2, or x, or the sine of x1. These are all nonlinear terms that would preclude us from well, actually, we are still able to use general linear least squares, even though we're not able to use the simpler version of linear least squares. And so both of these can get categories. Are we can use linear regression, and I'll just emphasize the general general linear regression, general least squares. Okay. And then finally, there are other variables that we can't do this to because they're not linear with respect to parameters. And so you see here we got a square of this parameter, or parameters multiplied by one another, or 1 over a parameter. And so these will require nonlinear regression. And so it's important to recognize that, because in biology, many of the equations that we deal with are nonlinear, and so we need to look at nonlinear regression pretty frequently. So let's take a look at what nonlinear regression is going to be about. Say you got a time course where you've measured drug after it gets injected, and you're measuring how much drug is in the blood over time. So it goes up and it comes back down, and you measure at these circles right here. And so what we're going to be doing is trying to find the model and the parameters for that model that best fits the data. And so you can see here, this blue line is a pretty darn good fit to the data. So we're going to be looking at how do we get this blue line fit that helps us model what happens in the bloodstream and calculate what would happen at future times. So the general outline here is that we have we're going to minimize the sum of squared errors between various versions of the model, in which we have a model F and data Y. Okay, and so we're going to be trying out different parameter values that go into that model. And we're going to be trying to find out what are the parameter values into that model that would make the sum of squared errors as small as possible, which would mean to get the blue line as close as possible to this data point. The general approach is that we're going to define our model, my model. We're going to create a function for the sum of squared errors that depends on the data and the model. And then we're going to use optimization to find the parameters that minimize the sum of squared errors. Okay, so a few things that you need to watch out for in nonlinear regression that you didn't need to worry about before when we're dealing with linear regression. Remember, when we looked at linear regression, it was guaranteed to find a single solution, at least if it was determined. Okay, but in nonlinear regression, there's no guarantee that you will find the global minimum that you're looking for. And in fact, there may be multiple minima in the space. So let me draw out what that would look like. So if you've got a sum of squared errors in P, this could be a surface that looks like this. That's kind of complicated. And so this could be a global min, which is what you might be looking for, and that would be where the parameters are the best fit. But your algorithm could get stuck in local minima and you're going to have to know how to deal with that. And one of the ways in which you can at least detect whether you're likely to be in local minima is try multiple initial guesses for the initial parameter values that you try, and also vary the tolerances or other features of your algorithm, because you even though it gets down to an answer, it's going to tell you an answer, you really don't know for sure whether the answer is the best answer that it could give you. Okay, so that's the one of the main things to watch out for nonlinear regression. So let's take a look at how this works. And so I'm going to talk about three main methods that are all different strategies for finding this minimum in a function. And I'll just do it very briefly here and then in more detail subsequently. The first is brute force minimization, in which you basically just try all the possibilities and then see which one works best. The steepest descent is one related to the steepest descent optimization algorithm that we looked at earlier a couple weeks ago, in which we look at the gradient of this function and use that to narrow in on the minimum point here. And finally, the Newton's method uses the Newton's optimization method to find the minimum, sometimes even more efficiently than other strategies. So let's take a look more closely at how this would work. So the brute force approach means to manually or programmatically just try all the combinations of the parameters. And so its advantage is that it's simple to implement. Okay, and you can get even coverage of the parameter space. However, it has a disadvantage in that it can be very costly. Okay, and so the basic idea here is that if you had some parameter p, and then you would just try at each of these values, okay, and then you just by brute force find even right here you would see this one is pretty close to the minimum, and this is another one that's very close to the minimum. So that's what the brute force method is about, and so you would implement that as a for loop. Okay. One disadvantage, in addition to having it being very computationally costly because you need to try all the options, is that you've only tried all the options at that certain resolution. And so it's not clear once you find an option if you have to further repeat this process in a more refined way. That is one way to kind of improve on the brute force approach. Okay, so here's an example of what this would look like in Python, a little bit of code. And so say we have these data points right here. Is obviously a very simple example. And so what we would do is we would first define time and the data that's coming in, where the circles are. And what we're going to do here is we're going to define a function that is p times t. So it's a linear function with one parameter. And then we're going to define another function that's a sum of squared errors. And that's going to be given by the data minus the function squared. And then we're going to sum all those together. And then in brute force parameter optimization, all we're going to do is create a for loop where we're just going to try every single option of the parameter and see which one works best. And so if you do that, if you tried all of these different values, you would find that at p equals 5, the sum of squared errors is the minimum. And so then if you plug in p equals 5 into the line, you find that yes, you indeed fit the data very well. And so that's a brute force minimization. And I'll be providing code for you, this code for you, so you can get a better handle on that on your own time. So that's one approach, is brute force. It's very costly though, and so the other approach to nonlinear regression is to use optimization methods. And so optimization methods are designed to efficiently search through the possible parameter space and combinations to find a best fit parameter set. Oops. That minimizes the error between the model and the data. And so it's trying to find a set of model parameters. Okay. And so most optimization methods, and what we mean by optimization methods are more strategic or kind of strategies to get to the very kind of area that you want. And in this case, before when we used optimization, we were usually trying to find maxima. And in this case, we're trying to find minima. And so most optimization algorithms are based on using the gradient of the sum of squared errors, because that shows the direction in which you can change the error depending on how you change the parameter values. Okay, so the first of these is called the steepest descent for nonlinear regression, and this is really just the same thing as steepest ascent optimization. It's just now we've got a minus sign instead of a plus, so that's going to help this find minima rather than maxima. And the basic idea here is that it's going to compute the direction of steepest slope, and then the parameters are adjusted with a step size proportional to that, to the magnitude of the gradient. Okay, and so basically, if you started right here as your initial guess, it'll take a big jump because the slope is steep, to P1, take another jump to P2, and get closer and closer. One of the disadvantages of this method is that as you get closer and closer to your minimum, then the slope becomes less, and so because the slope is less, then the gradient is less, and then so you start slowing down how closely you converge. So it's noted that it converges slowly at the end. And this is the same exact phenomena that we discussed when we were using steepest descent for optimization. So as a way of countering this negative, people also use the Newton's method. So Newton's method, again, this is the same thing that we were dealing with when we're talking about optimization. It's just what we're optimizing now is a sum of squared errors. And so at each iteration, we're looking at the gradient of the sum of squared errors, which is the first derivative. And we're also computing the Hessian. The Hessian is like the second derivative. Are taken. And the basic idea of this is that by doing it not just on the gradient but also on the Hessian, we're going to be able to take larger step sizes, because looking at the ratio of the gradient and the Hessian. And so what we find here is that typically what happens is that maybe the first few iterations aren't so fast, but it is able to very efficiently converge on the endpoint, the optimum at the end there. So that's the basic idea for Newton's method. And so because the steepest descent and Newton's method each have advantages and disadvantages, there's actually what's called the Levenberg-Marquardt algorithm, which is the most common algorithm for doing optimization in real practice. And so basically it's a combination, it's a hybrid between the steepest descent and Gauss-Newton algorithm, where at the very beginning it looks more like the steepest descent. It takes big jumps, but then as it starts detecting that the gradient is not changing is getting shallow, then it weights more towards looking at the Hessian of that, and then it is able to converge on a nice solution. And so this is a hybrid method that combines advantages from both approaches. And in Python, it's the curve fit algorithm. The default uses Levenberg-Marquardt, and we'll be looking at that here. So this is how you use the Levenberg-Marquardt or nonlinear regression in Python. It's going to be very compact here. All you do is you're going to define your t. It's our independent variable and the data, which is where the circles are. We define a function that we want to fit. In this case, we're just fitting a line to make it nice and easy. And then we're going to call the curve fit function, where curve fit needs a function that we define here, and it requires the data that you want it to fit. And then it'll pop out this p opt is the optimum parameter. Okay, and it finds that the optimum parameter p is 5. And so then I plug that back into a line and showed that this actually does in fact be a good fit. That's actually a very important point, is you need to prove to yourself that this is actually in fact having a good fit at the end. Because if you got stuck in a local minimum instead of a local maximum, or if you got stuck in a local minimum instead of a global minimum, then you could end up with a line that is very far from your data. So to summarize this section, we found that nonlinear regression can perform best fits even when the model is nonlinear with respect to parameters. That nonlinear regression cannot guarantee a global minimum. It may converge to a local minima. And so that's why it's very important to plot your data and make sure that the solutions make sense. And also, it can make sense to try multiple guesses of your initial conditions or initial parameter values. And finally, optimization methods such as steepest descent or Newton's method can make optimization more efficient than brute force strategies. So now at the very end here, I thought we could switch over to Python and just show you how these codes work. Excuse this. Okay, so I've got this file called curve fit examples that I'll be providing you. And the basic idea here is you see we're going to import NumPy, Matplotlib, and we're going to import the curve fit function from the SciPy optimize library. And so in this first section, we're setting it up where we've got t is the time range and a data range. Here I'm just making the data kind of linearly spaced, but we could change this to make more interesting looking data. And then we define the function. In this case, we're defining that the function that we want to fit is a line. And then we defined a sum of squared errors function that would quantify how far the data are from the predictions from the model. And so in brute force optimization, we are going to just loop over a range of parameters from 0 to 10. And and see what happens. And so I'll just run this bit of code. Okay, and what you can see is that it looped over and it plotted the sum of squared errors for each of the parameter values that it tried. And you can see here that at p equals 5, that's the minimum of this space. And so that means that p equals 5 is the best fit parameter. Okay, and then in contrast, we'll look at the Levenberg-Marquardt version or nonlinear regression version, where we're going to use the curve fit command, uses the same function t in data, and if I run this, we can see, here we go, it took a little while, and then I plugged in p-opt back into the function to show that we did in fact get a very nice, good fit to that line. So hopefully this code will help explain this to you, and also can give you a head start on the homework assignment. So thanks, this has been fun, and I hope this was useful to you. Take care.